Hello and welcome to the NPTEL MOOC on Applied Electromagnetics for Engineers. In this module, we will consider a few conceptual problems and conceptual questions that are associated with transmission lines, which you might have after going through the previous modules. And then we will also consider a couple of paradoxes, or at least one paradox that I talked to you about already, and the resolution of this paradox. Let us begin by revisiting the topic of characteristic impedance. What is characteristic impedance of a transmission line? We have defined characteristic impedance of a transmission line, denoted it by Z0, when in most cases we consider are the transmission lines without any losses. So, in which case Z0 will be completely real, and you can, instead of calling it as characteristic impedance, you can call as characteristic resistance and denote it by R0. Okay. But nevertheless, what is this characteristic impedance? We have so far not offered a definition of characteristic impedance, except to point out that when we solve the transmission line equations, that is how the voltage is changing and how the current is changing through the transmission line, it is possible for us to define the ratio of the forward going voltage, that is V0 plus, along the transmission line, and a forward going current I0 plus along the transmission line. The ratio of these two is what we called as the characteristic impedance, right. We could also consider the other scenario. I could put my source at at one particular end and then extend the transmission line all the way from Z equal to 0 maybe towards Z equal to minus infinity. Okay. Here, once I excite the transmission line, that is once I connect the source, there will be backward travelling voltage wave V0 minus and a backward travelling current I0 minus. Backward in the sense that it is going from Z equal to 0 to Z equal to minus infinity. Again, minus of this ratio will tell you the characteristic impedance. In a case where we have a finite length transmission line, which is what would happen in practice, then you will have both forward going as well as backward travelling waves V0 plus and V0 minus, in which case to define characteristic impedance you pick either forward going voltage and forward going current and take their ratio, or pick the backward travelling voltage V0 minus and negative of the backward travelling current, that is minus I0 minus, and that ratio will again be equal to characteristic impedance. Now, this is a straightforward definition. In literature you will find Z0 defined by other methods. Consider for now that I have a source here at Z equal to 0, and then I have a long transmission line stretching all the way towards infinity. Okay. So, my source is kept at Z equal to 0 and my transmission line is kept all the way to infinity. Okay. Now, supposing I chop off the transmission line at a particular point. Okay. So, imagine that this is my transmission line. Okay. I cut my transmission line here and replace it with the impedance, that impedance let me call as Z0. Okay. I can of course replace it with whatever impedance that I want, but let me choose a particular value of the impedance such that when I connect the source and excite the transmission line, I do not see any reflection back. In other words, that impedance with which the transmission line will be terminated or must be terminated in order to cause no reflections is called as the characteristic impedance. Okay. So, this is another definition of characteristic impedance that you would actually find. Of course, mathematically another way in which you can define the characteristic impedance is to take the ratio of the line impedance per unit length, that is Z, and admittance Y of that one, and then take the ratio of Z by Y. That will also denote the characteristic impedance. Okay. So, regardless of what definition that you adopt, it should be clear that characteristic impedance is actually a quantity that is completely specified by the characteristic constants of the line, that is the distributed constants of R, L, C and G that corresponds to a given transmission line will determine what is the characteristic impedance. Usually there is another question that comes up to one's mind, that if I consider a lossless transmission line, so why would I use a lossless transmission line? Obviously, I do not want any kind of an energy to be wasted in the transmission line that I connect between the source and the load. Okay. So, for that reason I will have to consider lossless line. Whether it is realizable in practice or not, it is a different question, but at this point consider a lossless transmission line. And what is the characteristic impedance of a lossless transmission line? it is given by the ratio of L to C, square root of L by C is the characteristic impedance. Now you might immediately ask, well, Z0 for a lossless transmission line turned out to be real, and real impedance is nothing but resistance. But resistance, as we have learned from our basic circuit theory, implies dissipation of the power or dissipation of the energy. How could a lossless line be considered equivalent to an impedance or equivalent to a resistance? The answer is quite simple. You have to again go back to the characteristic impedance definition. That is the impedance which is seen by the source when it is connected to an infinitely long transmission line, because on an infinitely long transmission line I only have forward going voltage and forward going current. My source is kept at Z equal to 0. So, I only have forward going voltage and forward going current, and that ratio is the characteristic impedance. Now, for a lossless transmission line, suppose imagine that you launch a certain amount of pulse energy into it, or launch a pulse onto the transmission line. This pulse begins to propagate from Z equal to 0 and keeps going all the way up to infinity. When would the pulse return back to the source? After an infinite amount of time. So, in effect, this pulse that you have launched on the transmission line moves all the way to infinity and never comes back. So, for as long as as far as the source is concerned, this energy that is represented by the pulse is simply lost. It is like a black hole. The transmission line is acting like a black hole because it is not going to give you any return pulse or return energy. But you might object, well, this is the case for an infinitely long transmission line, and in practice you do not have an infinitely long transmission line, and you will be right. So, consider a finite length lossless transmission line. What is the characteristic impedance of this one? This is the impedance with which you have to terminate the line, right, so that there are no reflections. So, if I take a finite length transmission line, terminate in its own characteristic impedance, I obviously, when I send a pulse, that pulse is completely absorbed into that load Z0 that you have connected, and no pulse comes back, because line terminated with its own characteristic impedance will give you no reflections. That is another definition of the characteristic impedance, right. So, as far as the source is concerned, again the energy represented by this pulse is completely lost, because it is not getting anything back. Okay. So, it is completely lost, and the case is the case is identical to that of an infinitely long transmission line. So, because of these reasons, we represent the characteristic impedance of a transmission line can be represented by a resistance or by a pure impedance, pure real impedance. Okay. Let us come back to another paradox that we talked about. This paradox was the possibility that if I connect my source onto an open circuited transmission line, there is a possibility that my V0 plus could have become larger. In fact, it would have become infinity when I consider a particular length of a transmission line. If I consider a lambda by 4 length of a transmission line and connect a source to it and monitor the output voltage on the oscilloscope and do the calculations in order to find out what is V0 plus, that V0 plus would turn out to be infinity. Of course, in practice you do not find infinities. If that you could have found, it would have been very nice. You could have drawn power, kind of perpetual motion you could have performed without spending any amount of energy, which is clearly not possible. So, what is the resolution for this paradox? I told you that the resolution for this paradox happens either because the line is lossy, okay, or even if the line is lossless, then source that you consider will have a internal resistance Rs. Okay. We will do a short calculation. I will leave the steps for you to verify that one later in your leisure time, but follow the argument to resolve this paradox. Incidentally, this paradox is also sometimes called as Ferranti paradox, and that was something that was observed in practice, not infinity, but a larger voltage than the launched voltage was observed in early power transmission systems. So, what is this paradox? Again, I connect a source. Okay, so I take my source, which could be a sinusoidal voltage, and I represent that source voltage by the phasor Vs. Please note this over bar, that is denoting the phasor voltage. To this I connect, or rather this voltage source has an internal resistance of Rs, which it must, right, which is then connected onto a transmission line which is uniform and lossless. At this end I open circuit it. Instead of denoting what is the length of the transmission line to a particular number, let me consider the general case, and you guys can verify what would happen if I keep changing the value of L. Formally, to calculate V0 plus, I know that I have to find out the equivalent circuit for this. The equivalent circuit would have the resistance Rs and the source phasor voltage Vs connected to the impedance that is seen by the source. This impedance Zin is nothing but open circuited transformed over the distance L or the length of the transmission line L. Okay. The voltage across this Zin is the voltage Vin, which we would like to calculate. We already know that an open circuited transmission line would transform into an equivalent impedance. So, this is the first step, right. So, I find out what is the impedance Zin of the open circuit transformed through a length L is given by minus j Z0 divided by tan beta into L. This Z0 is the characteristic impedance of the transmission line. So, this is the input impedance that I have. Then once I found what is Zin, it is very easy for me to find out what is the input phasor Vin. This is the phasor that would appear across the transmission line terminals, okay, across this equivalent circuit, from which we will calculate what is V0 plus being the amplitude of the forward going voltage. So, clearly this Vin we already know, this is nothing but the voltage that would exist here, and I know that voltage would go to a maximum and then it would follow this kind of a magnitude, would follow a magnitude of cos beta L kind of a thing. So, this voltage I know, this is measured at Z equal to minus L, at which point we are connecting the load. So, this is Z equal to 0 for the load position open circuit, and at Z equal to minus L is where I am connecting the source. Okay. So, this Vn is given by 2 V0 plus cos beta L. I hope that you are not wondering why I got this expression. Here gamma L is equal to plus 1, gamma L being the load reflection coefficient. Okay. Now, solving this, or equating the voltage, for this is the voltage Vin, but from the equivalent circuit what I get? From the equivalent circuit, this must be Vs bar Zin divided by Zin plus Rs, correct. You can solve this. I will leave this solution as an exercise for you to verify and get V0 plus as minus j Vs bar Z0 divided by 2 sin beta L Rs minus j Z0 cot beta L. Cot is nothing but 1 by tan. Okay. Now, this is an expression for V0 plus. Let us see if our earlier choice of L equal to lambda by 4 will lead to some sort of a infinity to appear. Okay. Consider two cases. I will consider two cases. One case will be to try and make beta L equal to pi by 2. Beta L equal to pi by 2 corresponds to the case of L equal to lambda by 4. So, when you substitute beta L equal to pi by 2, notice what happens. Yes, sine of beta L will become 1 because sine pi by 2, but what is cot beta L? I know that tan of pi by 2 goes to infinity, therefore, this cot beta L must go to 0. So, which means this entire term is gone, right, and this term has become equal to 1, and I just have this minus j Vs bar Z0 by 2 Rs, and if I only retain the magnitude of this voltage is given by Vs bar magnitude into Z0 by 2 Rs. I am assuming that Z0 is real. I am also assuming that Rs is just a resistive load internal resistance, resistive source internal resistance, and therefore Rs is also real. So, what we see is that for the case of L equal to lambda by 4, our output or our V0 plus voltage is actually equal to a finite quantity which is given by magnitude of the source voltage Z0 by 2 Rs. Now, when you put Rs equal to 0, obviously V0 plus goes to infinity, but clearly this is not a practical situation because all sources in practice have some internal resistance for which you have to account for. So, in a real case, Rs is never equal to 0, it could be low, but it could never be 0, and therefore V0 plus could be large, but it could not go to infinity. Okay. Consider another case. For example, we might consider beta L equal to pi. If I go back to this expression here, I know that sine of pi must turn out to be 0. but then the resolution for this is to completely expand this, okay, not just leave it at sin beta L, but to expand it, and you get cot of beta L and there is a sin beta L. So, cot beta L, what would happen? Cot is nothing but cos beta L by sin beta L, but when beta L is equal to pi, cot becomes infinity. So, there is an infinity here, there is a 0 here. So, that too have to become finite. So, when you expand it through the brackets, open up the bracket and expand it, this term will actually go to 0, this term will actually be, this term will go to 0, this term will go to 1, and what you get, again verify this case, that the V0 plus voltage, magnitude of this V0 plus would be magnitude of Vs divided by 2. Okay. So, you see again that there are no infinities. Let me introduce another parameter. We have not really talked about this parameter. We have assumed that the voltages that I am seeing on the transmission line would be a travelling voltage wave, right, of the form cos. So, it would be of the form cos omega t minus beta into z. Okay. Already I have told you what is omega. Omega is nothing but frequency, which frequency of the source, which is given by 2 pi into f. Omega is the angular frequency measured in radians per second, f is the frequency that is measured in hertz. An older notation for f was in cycles per second, but the modern SI unit for this is hertz. Okay. We have also seen what is the ratio of omega by beta. Omega by beta is the phase velocity, and this phase velocity will be equal to c in air, correct. In vacuum or in air, the phase velocity will be equal to c. Okay. Now, there is another parameter that we normally talk of, which is called as the wavelength. Okay. This wavelength is denoted by lambda, and it is actually given by the phase velocity of the travelling voltage, which would be up, right, divided by f, f being the frequency. You can substitute for expression of up from this one. So, you have the phase velocity being given by omega by beta. So, this would be omega by beta into f, but omega is nothing but 2 pi into f. So, divide this fellow by beta into f. Clearly f from numerator and denominator cancel with each other, and what you end up is that wavelength lambda is given by 2 pi by beta. Alternatively, you can also write beta as 2 pi by lambda. Please note that this lambda inside a material will change because lambda is dependent on up. So, this is one of the other things that you should remember. Suppose I consider air and I consider glass. Okay. If I launch light, or if I think of light as a photon, then the energy of this photon would be some h into f, where h is the Planck's constant. Okay. What would be the energy of this photon inside glass? Most people would think that the energy would be different, but actually the energy would always be the same, whether you are working in air or whether this photon is propagating in glass. So, the energy of this photon will be the same h of f in glass. In other words, the frequency when it goes from air to glass, the frequency of the photon does not really change, it does not change. What does change is the wavelength lambda, okay, because inside glass your phase velocity changes, and the ratio of phase velocity to lambda must remain constant because the frequency must remain constant. Therefore, if the phase velocity decreases, lambda actually increases. Why am I bringing up this photon picture is because if I consider a transmission line, which maybe is a coaxial transmission line. So, this is a parallel wire transmission line which is filled with air as a insulating medium in between, but on a coaxial cable I can actually fill this region between the inner core and the outer or the second copper enclosure by some material whose permittivity would be epsilon r, or the refractive index will be n. We will talk about this epsilon r and n. What it means is that the phase velocity here will not be the same as the phase velocity in the air, but that is all right for us because phase velocity usually reduces when I consider an insulating medium, but my corresponding lambda actually increases, thereby keeping the ratio to be constant and equal to f. So, I hope you understand the significance of this wavelength. Finally, we have talked so much about transmission line, but we have not answered. We will answer this question in much more detail with all mathematical ideas later on, but we have kind of not really told you is when to apply this transmission line theory. So, when do I need to consider a particular wire as a transmission line, or when do I treat this as a simple wire? I will just give you a 5-minute idea on when we consider transmission line theory to be applicable to the wires that we are considering in the experimental setup or in the actual setting up of the system, electronic system. You basically understand one thing, right? So, when we consider a particular piece of wire as a wire, we are not concerned about the time that is required for the voltage at one end of the wire to travel to the other end. That is, if I consider this as my wire which is connecting, say, one integrated circuit here and another integrated circuit at this point, of course it will not be like this, but imagine that way. When the IC changes its state, maybe it goes from 0 to 1, changing the voltage level from 0 to 3.3 volt. If the load has to correspondingly change, if the load is just kind of a inverter maybe for example, then the inverter input voltage must change accordingly, right, so that the output of the inverter must change. But this wire which I have connected, which is the interconnect that I am talking about, or the wire that I am considering, if the voltage change is immediately available at the input end of the next IC, then this wire can be treated as a wire because it has not introduced any delay, it has not changed the shape of the pulse that is being transmitted or kind of the voltage that is being transmitted. So, we consider as long as the velocity or as long as the delay introduced by this piece of wire to be very small compared to the rise time of the change of the state of the voltage source that is connected to one end, then we usually do not consider the wire as a transmission line. But imagine that my IC is changing and it is changing its state in about 1 nanosecond, whereas the delay introduced by this wire because of the length of the wire or the insulating material that I am using which slows down the velocity, the delay introduced by this wire may be about 10 nanoseconds. So, while the voltage at one end is changing from 0 to 3.3 volt, the voltage change does not immediately come over here because there is a considerable delay here, and that change will be visible to the load side only after 10 nanoseconds, right. So, the load will take some amount of time to see what is the change that is happening, and while this is happening, if the integrated circuit changes from 0 to 3.3, then falls back from 3.3 to 0, then this short duration pulse will not be able to be seen by the load side immediately. Okay, so that is essentially when you have to consider transmission line. So, in other words, since we are talking of pulses and a pulse will have a typical frequency spectrum, right, and let us say for our purposes this is the frequency spectrum that I am interested. So, this is along the f axis, this is the time axis, and let us say this is my maximum frequency of interest. Okay. But I can also imagine that instead of talking about the frequency, I can talk about the wavelength, then corresponding to this f max there will be a shortest wavelength over here. Okay. We say that an element is in the lumped regime when the length of the element is very small compared to the shortest wavelength of interest. So, if I consider this particular pulse of some duration t, then there will be a certain f max that one can consider, and corresponding to that f max there will be a shortest wavelength. Of course, there will be other wavelengths also here, but this is the shortest wavelength that you are considering. And if this shortest wavelength happens to be much larger compared to the length of the element. So, if this is my element that I am considering or just a simple wire lead that I am considering, if this length happens to be much smaller than the shortest wavelength, then we call this as a lumped element. Okay. Is there an estimate for the maximum frequency? Well, yes, the typical estimate for this maximum frequency is 0.25 by TR. There are a few conservative estimates which tell you that it must be 0.35 by TR. Depending on your application, you can pick this particular number. I will just pick 0.25 by TR as the estimate for the bandwidth of the pulse that I am considering. Okay. So, this bandwidth that I am considering will have the maximum frequency of 0.25 by TR, where TR is the rise time of the pulse. So, rise time being say maybe 0 to 1 volt in the normalized sense, whatever the time that is required for the voltage to change or the pulse to change is called the rise time, and let us say this is my rise time, and this is of course my transmission line that I am connecting. there is a time delay introduced by the transmission line, or let me call this as time of flight that is required. So, as I said, if Tf is much smaller than Tr, then this can be considered to be a wire. So, lumped means I consider this to be a wire. So, the length L must be very small compared to the shortest wavelength, but I can consider in engineering notation that L much less is actually meaning to be less than or equal to 0.1 times the quantity. So, when I say that A person's height is very small compared to B person's height, my engineering notation is that the height of A is only about 0.1 times the height of B. Of course, that case is not very nice analogy, but you think of this case. Okay. So, less than or far less is less than or equal to 0.1. Okay. So, this is when I consider it to be a lumped regime. So, whenever my length is much smaller than 0.1 lambda short, I consider this to be a lumped regime, but I know what is lambda short, I know what is the maximum frequency. Assuming for now that I am working in air, or the phase velocity is c, the corresponding lambda short happens to be c divided by maximum frequency, which happens to be in this particular case 0.25 by Tr, right. So, this would be c divided by 0.25 by Tr. Since 1 by 0.25 will go to 4 times c by Tr is the shortest wavelength, and L being less than or equal to 0.1 times 4 c by Tr, this right hand side quantity is nothing but 0.4 c by Tr. But length is L, right. If I divide this length by, or rather, so I have 0.4 c by Tr. So, if I take this c here, okay, which is the speed to the denominator of the left hand side, then I get L by c, which happens to be the time of flight from one end of the wire to the other end of the wire. So, my condition for lumped regime is that Tf must be less than or equal to 0.4 divided by, or rather 0.4 into Tr. So, this is not, I guess I made a small mistake over here, this should have been 0.4 c into Tr. So, this should actually have been 0.4 c into Tr in the numerator. So, this is actually 4 c Tr. So, please correct this one. So, I get Tf to be less than or equal to 0.4 Tr. On the other hand, my condition for something to be considered as a distributed or a T-line effect would be the other way around. That is, I consider some wire to be important in terms of the transmission line effect when the length of this wire will be greater than or equal, much greater than lambda short. Okay. But what is much greater than? Much greater than can be interpreted as 10 times the quantity on the right hand side. Therefore, when L is much larger than 10 times lambda short, but I also know what is lambda short. Lambda short is nothing but 4 c into Tr into 10 will give me 40 c into Tr. So, when the length of the wire is greater than 40 times Ctr, then I consider it to be a distributed regime. So, I can actually plot both Tr and Tf on this particular axis, and you see that this region corresponds to lumped region and this region corresponds to distributed region. With this, we stop here and consider other effects in the next class. Thank you very much.